Hi, this is part 2 of the lessons using PWM in the PIC microcontrollers. In the previous videos, we have already talked about the two key characteristics of a PWM or a pull width modulations, that is the duty cycles and the periods. The duty cycle is the on times of a PWM, and the period is the amount of one pulse, the times for one pulse. Then we have already did some experiment with a PWM effect on the motors, where we can generate pull width modulation pulse to switch on and off a switch to make the motor run faster or slower. In this video, we will consider how to use a PWM in a PIC MCU. So this is a hardware, a circuit inside a PIC microcontroller that generates a pulse width modulation outside a pins of the microcontrollers, where they name it like the PWM1 or PWM2 or PWM3 or 4 or something. You can check for the datasheet the pin diagrams of a microcontrollers, PIC microcontrollers right here, and then the table, period allocation table, to see where is it all located. For example, the PWM number 3 at the RA2, and PWM number 1 for RC5, and PWM number 2 for RC3, and the last one, PWM number 4, located at RC1. So the microcontrollers PIC16F1509 have 4 PWM pins. Okay, in the datasheet, it tells me that we can write the value to a register where the PWM X stands for 1, 2, or 3, or 4. PWM X and then DCL and DCS, these two registers combine together to make a 10-bit value to make the duty cycle. And to change the period or to set up a period, we have to configure timer 2 and then the PR2 register of the timer 2 to make the period. Take a look at the datasheet. It tells us that the period formula would be period equal to PR2 register. Remember, it is 8-bit register plus 1 and then multiply with 4 and then multiply with the oscillation of the system and then multiply with the prescaler of the timer 2. And pull width modulations is the 10-bit register multiplied with the oscillation, the system oscillation, and then the prescale of the timer 2. We can do some calculations here where just an example. For example, we take 1 megahertz, 1, 2, 3, 1 megahertz right here as the system oscillations, and then we can have the t or the amount of times for this one. It is in second. Okay, if you want to take it in the microsecond, you would multiply with this one, multiply with 100. Okay, it is 1 microseconds. Okay, that's it. And then you write for example 100 to the PR2, and the prescaler would be 1, and then you will got the period would be this equation. This one take plus 1 and then multiply by 4, and then this one like this one take the plus 1, okay, and then multiply by 4 and multiply with this one and then multiply with the rescaler. Okay, it's a 404 microsecond. So the periods or the pulse take 404 microseconds. You can change it to the other number to take, for example, this. So remember 1 kilohertz would take 1 millisecond and then would take 1000 microseconds pulse. Okay, so if we would like to have this one or 1000, we have to calculate the number for PR2. Okay, for example, we can take the value here. This is the wanted values or 1 kilohertz. We can recalculate it by this one is this value divided by this one, divide by this one, multiply with 4 and multiply with the this one and then minus 1. Okay, so we take the value for 249. So if we write the value 249 to the register PR2, we will get the period of 1000 microsecond or 1 kilohertz. Okay, that's the way we do for the period. And also the pulse width, we have the similar formulas here where the pulse width take the 10 bits register, take the multiply and another multiplies. So if we take for example 50% of duty, all right, then this one would be 500 microseconds, right? Then we have to write the value of 500, oh sorry, this one divide by this, multiply with this. Okay, it's 500. Then we have to write the value for 499. Okay, it is because the register is take the value, the first value for 0 and the last values for 10 bit would be this one 1023. Okay, this is for 10 bits register, so it take the first value for 0% would be 0 and then the half or 50% would be 499, not the values 500. Okay, this is the formula for us to calculate. Then we have the resolution of the duties. Remember that we have the system oscillation for 1 microsecond, so we cannot generate the pulse width modulation with the resolution faster than this. Faster than this, this means that 0.5 microsecond or something. This is not possible. So if you take the period for 500, for example, then you got only from 1 microsecond to 500 microseconds only. So the resolution may decrease to 9 bit also, 9 bit, because 9 bit is equal to 9, equal to the maximum value would be 912, but we will limit it to 500, or actually it's the 499, because the fastest pulse we can generate is the system clocks is 1 microseconds. Okay, so this is a formulas for the resolution. If we use the MCC, the code configurators, it will automatically calculate it for you, the duty cycle and the pulse width modulation periods. We will do some examples. Here is my already created empty projects where I have my main files here, nothing in here. Then I can use my MCC. I open my pulse width modulation PWM1, okay, the PWM, but I have to take out the timer 2 for the period right here. I would take it 1 millisecond for the period. Okay, the prescale I take 1. So then I can open my PWM modules. Then I will see my frequency would be 1 kilohertz. If I change the timer to for example 5 microsecond, 500, okay, then I would see the frequency of the PWM would be changed to 2 kilohertz, or the period would be 500 microseconds. Alright, then my maximum value for the duty 100% would decrease to 499. For the maximum value would be 500. If I change it to 1000, it means 1 kilohertz. It means from 0 to 100, 1000, sorry. Then my value would be from 0 to 1000. Actually, it's 999 for 1000 values. Okay, and then the frequency here would be 1 kilohertz. Then I open my pin manager, and I can see that I have another PWMs. Would be PWM1 would be located at the port C5. So I take the lock on it to make use of the PWM at this pin. Then if I satisfied it, then I can generate. Okay, I have the PWM and the timer 2 functions. Okay, then it's PWM initialize, and it writes some value here. So you can see here the PWM1 DCH and DCL already calculated the values. Then we have the function load duty value with the DCH and DCL changes with the value we loaded here. So, but it will calculate it automatically for you. If you open the timer 2 for the PR2 register, you can see that already calculated for you for the value of 249, or right here is 1000. It would 249. Okay, that's it. That is the value. Then we got nothing else here. Okay, then we can generate. Okay, and then we can build. Okay, you can see here is my main function. I do nothing. The pool width modulation will automatically generate it for me. Okay, let's take an example for 50% of the duty cycles. Then you generate. Okay, and then you build it. Okay, then let's upload the code right here for 1 megahertz system frequency. Okay, I connected the PWM to the virtual oscillator to check whether it's work or not. Okay, then you see here the pulse. All right, let's count. All right, it's a 1 unit for 0.5. So you take the periods of 1 kilohertz. Okay, 1 kilohertz pool generated the channel B of a oscillation. Okay, you can change it to 90. Okay, for example this, and then generate it. Okay, let's check it. Oh, sorry, remember that you have to generate. Okay, and then rebuild. Don't forget the generation. Alright, and then we generate it. So now the pulse got to 80%, okay, with the same periods as before. Also, you can change the timer 2 for 2 kilohertz, or you change to 500. Alright, and then PWMs for 90 or 30s. Okay, then the resolution decreased to 8-bit. Alright, oh, I forgot the generation. Okay, and then rebuild. Okay, and then check it again. Okay, then you see here is 30%. Okay, with the pull width modulation would be 1 2 2 and oh sorry, take it one shot. Okay, and then you see 1 2 3 4 5 unit with 0.1. Okay, so it's 0.5 milliseconds. So that's it. That's how we use the PWM with the MCCs. It's very easy and very simple. Then can we take a look at the exercise? Okay, we have the exercise here where I use the modules L298 drivers to drive a motors. Then we have the requirement that we have 5 buttons. Button number 1, motor stop. Button number 2, motor run at 50% of PWMs, or half speed of the max speed of the motors, and so on. Button number 3, 75 PWMs. Button number 4, 100%, and then the motor run at the counterclockwise or the clockwise. This is change the rotation of the motors. Button number 5. So we take the fourth button 1 to 4 first. Where we want to stop the motor, we simply write the 0% PWM. I have already designed a circuit here where I connect the S1 to RA5 and S2 to RB4 and so on, and then connect the motor driver here with the in1 to RC0, in2 to RC1, and PWM already connected. Remember that the L298 controls like this, where you have the in1 and in2. If you take the high value to in1 and low value to in2, you got the motor run forward. And you take the low to the in1 and high to in2, you take the reverse. So in1 and in2, right here, take the rotation of the motors. And then if you take the enable pins for the PWM low, it will release the motors. It will stop the motor. And then you take it high, it will run as forward or reverse or clockwise or counterclockwise. It's very easy driver motors. Okay, let's take the programmings. Okay, first I want to use the define to make it easier for me. S1 as the port A bit dot RA5. Okay, and define S2 port B bit dot RB4, and so on. I can copy it. Oh, sorry. Okay, this is 3, 4, and 5. 5, 6, and 7. Okay, and another define for in1 lot C bit dot lot C0 and lot C1 for the in 2. Okay, let's open the pin manager and then take the port C and port C1 output, and then the others port P for input, and then the port A RA5 for input. Okay, then we generate it. Alright, let's open again the main files, and then we take the while loops here. We check the buttons. If S1 is press, okay, where is my hardware? So when I press, the button will read as 0 1. Okay, so take it here is 0 as it presses. Then I load the PWMs right here. Copy is 0. My main file is here. Alright, for 0. Then the motor will stop when pressing S1. Alright, I want to change it to the 1 kilohertz. Okay, and then the PWM here, the maximum value would be 999. Okay, the 50% would be 499. Okay, so regenerate it. Okay, and I take the copy for my S2 press for 50% 499. Okay, motor will run 50% PWM. Okay, press S2, and similar to S3 and S4 for S3. Okay, 3 4. Okay, what is the other values for the 75? 749. Okay, sorry. Oh, my main programs 749, and then 100% 4999. Okay, save it, compile it. Or before it, I have to stop the motors. Okay, rebuild. Make sure that you generate it before you rebuild. Okay, and then rebuild. Alright, let's check. Okay, the motor stopped. Oops, I forgot to set the in for the rotation. I take the in 1 is 1, in 2 is 0. Okay, otherwise it will not rotate it. Let's check. Okay, and then press the buttons. Okay, for 50%, S3 for 75, S4 for 100, and this one for stop 50%. Okay, 70. Okay, 100. Okay, the speed of the motor will change. Okay, then we will program the last one, the button number 5. So the requirement is every time I press the button, it will change the rotation. So I need to change the in 1 and in 2 of the hardware here. So I change it to 1 and to 0. So I have here the S5 when it release. Okay, and then press, sorry, and then release, and then press, and then release, and then press it again, and then press, and then release, and so on. Okay, and then I have my motors for the CW, okay, rotation, and then the CCW, okay, where at the first start it will CW, and then the first fresh will make it the counterclockwise, okay, and then go to the second press, it will change the rotation, okay, and then the third press will make it change the rotation again, okay, and then the fourth press like this, okay, and so on. So we have here the phase number 0, phase number 1, phase number 2, phase number 3, and then we repeat the phase number zeros here. Okay, so my system of S5 will have 1, 2, 3, 4 phase, and then repeat it 2, 3, and so on. So we have 4 phase from 0 to 3 for S5. Then we can declare a variables for phase S5 phase, okay. The initial state would be 0, so I take it unsigned chart S5 phase, okay. Then I check it if S5 is pressed, okay, and the S5 phase currently is 0, alright. Then when the user is pressed right here, okay, take it here, it will change the phase from 0 to 1, alright. Then the S5 phase will change to 1, okay. Then the user, they release the buttons, this is the release signal, the phase will change to number 2, okay. Take release, and then if the phase is phase 1, then we change to phase 2, okay, and so on. The second press with phase 2 will take it to the phase 3, and then the last release will take it to the phase zeros again. So we take phase 0, 1, 2, 3 and 0, 1, 2, 3. Then we can handle the output. If the S5 phase equal to 0, then I want to output the clockwise. Alright, take it as the in 1 is assigned to 1, and then in 2 assigned to 0 for the clockwise CW, okay. And then my phase, if I take it to 1, then the motor will change it to from CW clockwise to the counterclockwise, or I change it here 0 to 1. Alright, how about the phase number 2? In the phase number 2, also the counterclockwise, so I take it 0, 1 for counterclockwise, okay. And the last one, phase number 3. For my phase number 3s, I take the clockwise, then the clockwise here. So that's it. This is my checking for phase, okay, and this is the output of the phase. Let's check the buttons. Alright, we simulate it, okay. So we take the half speed, okay. We take the button press, okay, I press, and then it changed the rotation, and then another press we take the reverse of the signals here, and then another press. Okay, and then another press. So S5 phase will rotate it from 0 1 2 3 0 1 2 3. Okay, take it another times, change the speed. Okay, all right, so that's it. That's my first example, or exercise 1. I hope that you can do the similar one with one button that controls, that will increase the PWM for every press, will increase it 20%. Okay, and then another exercise, that you read the potential meter for 10K. You read as the ADC, or analog signal, and then you convert it as an analog signal into the PWM of the motors. Then you might display that on the LCD, the character LCD, to review the old lesson. So that's it. Thank you, and see you in next lessons.